the factory that turns batteries into cars. So you want to own a Tesla factory. Imagine owning a massive facility capable of producing hundreds of thousands of electric vehicles every year. Robots weld metal around the clock. Gigantic presses stamp body panels in seconds. Battery packs move across automated production lines. Software is installed into every vehicle, and every few minutes, another finished car rolls off the assembly line. From the outside, it looks like the future of manufacturing. Electric cars, robots, artificial intelligence, gigantic factories, and billions of dollars in technology. But behind every Tesla is a brutal manufacturing equation. Steel costs money, aluminum costs money, lithium costs money, battery cells cost money, workers cost money, factories cost money. And the biggest problem is this: you can build one of the most advanced car factories in the world and still lose money if you can't produce enough cars at the right cost. So the real question isn't how many Teslas a factory can build. It's how much money remains after paying for the batteries, raw materials, labor, machinery, logistics, research, financing, and the billions of dollars required to keep the factory competitive. To understand that, let's build the economics of owning a Tesla-style electric vehicle factory from the ground up. Which Tesla factory are you buying? First, we need to understand what kind of factory we're talking about. A modern Tesla manufacturing complex isn't just a building where workers assemble cars. It can include body production, battery pack assembly, paint operations, final vehicle assembly, testing, warehousing, automation, and in some locations, nearby battery or energy production. For this model, imagine owning a massive electric vehicle factory capable of producing approximately 500,000 vehicles per year. That's an enormous level of production. The facility requires stamping machines, body shops, robotic welding systems, paint facilities, assembly lines, battery pack production, testing equipment, warehouses, internal transportation systems, and massive amounts of computer hardware and software. This isn't a car workshop. It's a giant industrial machine designed to turn billions of dollars of equipment and materials into hundreds of thousands of vehicles. And building that machine requires serious capital. The first $5 billion. Now imagine building and equipping a large modern EV manufacturing complex requires around $5 billion in total investment. The exact cost would depend on location, production capacity, land, automation, battery integration, local construction costs, and infrastructure. But $5 billion gives us a useful model. That money goes into the building, production lines, robots, stamping presses, paint shops, assembly systems, battery equipment, testing systems, warehouses, power infrastructure, and thousands of specialized machines. But construction isn't the only cost. The factory also needs working capital. Before the company receives money from selling cars, it may already have billions tied up in batteries, electronics, steel, aluminum, glass, tires, motors, and other components. Suppose another $1 billion is required for working capital and production ramp-up. Now, roughly $6 billion is tied up before the factory reaches full production. The first problem isn't making the car. It's surviving long enough to build enough cars to justify the billions spent creating the factory. From raw materials to a finished Tesla. Now the manufacturing process begins. Large coils of steel and aluminum enter the factory. Gigantic machines stamp them into body components. Robots weld those components together to create the vehicle structure. The body moves into the paint shop. Then comes the battery. Cells are assembled into modules and packs, depending on the manufacturing design. Electric motors are prepared. Wiring systems are installed. Screens, seats, glass, doors, suspension components, software, and thousands of other parts are added. At the end of the line, the vehicle goes through inspection and testing. Then it is prepared for delivery. The finished car may look simple from the outside, but inside is a combination of mechanical engineering, battery technology, electronics, software, and automated manufacturing. Every Tesla is the final result of thousands of parts arriving at exactly the right place at exactly the right time. One missing component can delay an entire vehicle. The battery cost problem. Now we reach the most important economic issue, the battery. In a traditional gasoline car, the engine is one of the most valuable components. In an electric vehicle, the battery can represent a major portion of the vehicle's manufacturing cost. Imagine our factory produces 500,000 vehicles per year. If the average battery system costs $10,000 per vehicle, that represents approximately $5 billion in annual battery costs alone. And battery economics can change. Lithium prices move, nickel prices move, other material prices move, battery cell technology changes, and suppliers negotiate prices. A $1,000 increase in battery cost per vehicle would add another $500 million in annual costs across 500,000 vehicles. When you build 500,000 cars, a small cost increase per vehicle doesn't stay small for long. It becomes hundreds of millions of dollars, the raw material problem. But batteries aren't the only major expense. Every car needs steel, aluminum, copper, glass, plastic, electronics, semiconductors, rubber, interior materials, and thousands of other components. Imagine the average raw materials and purchased components for each vehicle costs $25,000. Across 500,000 vehicles, that's approximately $12.5 billion per year. Now imagine global commodity prices rise, or a major supplier increases prices, or a shortage develops. Even a small increase in cost per vehicle can destroy a large part of the factory's profit. Suppose costs rise by just $1,000 per vehicle. Across 500,000 cars, that's another $500 million in annual expenses. The factory may control its robots. It may control its production lines. But it doesn't control the global prices of the materials those robots need, the cost inside every car. Now, let's build a simplified economic model. Imagine the factory produces 500,000 vehicles per year. Suppose the average selling price is $45,000. That would generate approximately $22.5 billion in annual revenue. Now imagine the average manufacturing cost is around $38,000 per vehicle. Across 500,000 cars, that's approximately $19 billion in manufacturing costs. That leaves $3.5 billion before additional expenses. But the factory still has to pay for labor, maintenance, engineering, software development, sales operations, transportation, insurance, administration, factory depreciation, warranty costs, and financing. Suppose these additional costs consume another $2 billion. That leaves approximately $1.5 billion before taxes and other financial expenses. That sounds extremely profitable. But now watch what happens when vehicle prices fall. The price war. Electric vehicles are becoming increasingly competitive. Tesla may cut prices to increase sales. Competitors may lower their own prices. New manufacturers may enter the market. And consumers can become more sensitive to price. Imagine the average selling price falls from $45,000 to $40,000. At 500,000 vehicles, revenue falls from $22.5 billion to $20 billion. That's a $2.5 billion reduction in annual revenue. But the factory doesn't automatically become $2.5 billion cheaper to operate. The building still exists. The robots still need maintenance. The equipment still needs electricity. Employees still need to be paid. And the billions invested in the factory still need to generate a return. This is the brutal economics of car manufacturing. A few $1,000s of price reduction can erase billions in revenue. And that is why controlling production costs is critical. The automation advantage. One of the biggest advantages of a modern Tesla-style factory is automation. Robots can weld, lift heavy components, move materials, perform repetitive tasks. and operate with incredible precision. Automation can increase consistency. It can improve production speed, and it can reduce the amount of labor required for certain tasks. Imagine the factory spends billions on automation. At first, that sounds like an enormous expense. But if those machines allow the company to reduce manufacturing costs by even $500 per vehicle, across 500,000 vehicles, that's $250 million in potential annual savings. Over several years, those savings can become enormous. The robot is expensive once. The human cost continues every hour the factory operates. But automation creates another problem, the labor and automation problem. Automation doesn't eliminate labor. It changes the type of labor the factory needs. Instead of only needing assembly workers, the factory needs engineers, technicians, robot specialists, software experts, maintenance teams, quality control specialists, and production managers. And highly automated factories can become extremely complex. If a robot stops working, an entire section of the production line may slow down. If software fails, equipment may stop. If automated material systems experience a problem, parts may not arrive where they're needed. The more automated the factory becomes, the more expensive every major technical failure can become. Automation can reduce some costs, but it also creates dependence on highly complex systems. The production volume gain. Now imagine the factory can produce 500,000 cars per year, but fixed costs are massive. The factory may have billions invested in equipment. Those machines need to be maintained whether they produce 100,000 cars or 500,000 cars. This creates a powerful advantage for high-volume production. Imagine fixed factory costs are $2 billion per year. At 500,000 cars, that works out to $4,000 per vehicle. But if production falls to 250,000 cars, the same $2 billion in fixed costs becomes $8,000 per vehicle. Suddenly, every car has become $4,000 more expensive before even considering batteries and raw materials. The factory doesn't become profitable because it can build cars. It becomes profitable when it builds enough cars to spread its enormous fixed costs across millions of units over time. This is why volume matters. The capacity utilization shock. Now imagine demand weakens. The factory operates at only 60% capacity. Instead of producing 500,000 cars, it produces 300,000. Variable costs fall. The factory buys fewer batteries, less steel, fewer tires, fewer components, but fixed costs remain. The building is still there. The robots are still there. Management remains. Maintenance continues. Insurance continues. And equipment continues losing value through depreciation. A factory producing 40% fewer cars doesn't become 40% cheaper to operate. The fixed infrastructure remains. And now those costs are spread across fewer vehicles. This can rapidly destroy margins. The supply chain problem. A modern electric vehicle requires thousands of components. A single supplier failure can stop production. Imagine the factory has enough batteries, enough steel, enough motors, enough workers, but one small electronic component is unavailable. The car may still be impossible to complete. The factory now has unfinished inventory. Production schedules are disrupted. Workers may be waiting, and customers may have to wait longer for delivery. A car factory is only as strong as its weakest supplier. One missing part can stop a billion-dollar production system. That's why supply chain management is a major part of the economics. The technology problem. Electric vehicle technology changes quickly. Battery chemistry improves. Motors become more efficient. Manufacturing methods evolve. Software features change. And competitors introduce new products. Imagine spending billions building production lines optimized for a specific vehicle. A few years later, customers want a completely different design. The factory may need expensive upgrades. New equipment may be required. Production lines may have to be redesigned. In a Tesla-style factory, the equipment doesn't have to break to become obsolete. The market simply has to move faster than the factory can adapt. That is why constant reinvestment becomes necessary. The inventory trap. Now imagine the factory produces cars faster than customers buy them. Finished vehicles begin filling parking lots. Billions of dollars become trapped in inventory. And unlike a bag of fertilizer or a steel beam, a car can become less valuable when a newer model or lower price enters the market. If Tesla cuts prices after the factory has already produced thousands of vehicles, the value of existing inventory can immediately become a problem. The company may have to sell those vehicles at a discount. Inventory isn't just a parking problem. Every unsold car represents tens of thousands of dollars trapped outside the company's bank account. The energy and infrastructure problem. A giant factory consumes enormous amounts of electricity. Robots need power. Paint shops require energy. Climate control systems operate continuously. Machines run around the clock. Charging and testing systems consume electricity. The factory also needs water, transportation infrastructure, data system, and reliable connections to suppliers and customers. Imagine electricity and utility costs increase by 25% across a massive facility. That increase could represent tens or even hundreds of millions of dollars. Location therefore matters. A factory with access to cheap electricity, strong infrastructure, and efficient logistics can have a significant advantage. The factory doesn't exist in isolation. Its economics depend on the infrastructure surrounding it. The ownership traps. The first trap is assuming a famous brand guarantees factory profits. The second is underestimating battery costs. The third is building more capacity than demand requires. The fourth is ignoring price competition. The fifth is spending too much on automation without achieving enough volume. The sixth is underestimating supply chain risk. The seventh is allowing inventory to build up. The eighth is failing to adapt to new technology. The ninth is using too much debt to build the factory. And the final trap is confusing vehicle deliveries with profitability. A factory can sell hundreds of thousands of cars and still struggle if the profit per vehicle is too small. The factory verdict. So what separates a profitable Tesla-style factory from a multi-billion-dollar industrial experiment? Low battery costs, efficient production, high volume, strong capacity utilization, reliable suppliers, controlled automation costs, and the ability to reduce the cost of every car. The smart owner doesn't simply ask, "How many cars can this factory produce?" They ask, "How much does every vehicle cost to build? What happens if battery prices rise? What happens if vehicle prices fall? How many cars must the factory sell to cover its fixed costs? How quickly will the equipment become outdated? And how much cash will remain after billions of dollars in capital investment?" Those are the questions that determine whether the factory creates wealth or destroys it. The real economics. From the outside, a Tesla factory looks like a machine from the future. Robots build cars, software controls production, batteries replace engines, and enormous factories operate at incredible speed. But underneath all that technology is a very old economic problem. Can you produce something for less than customers are willing to pay? And can you do it at a large enough scale to justify the billions invested? A Tesla-style factory depends on batteries, raw materials, suppliers, automation, electricity, workers, technology, and customer demand. When production volume is high, costs can be spread across hundreds of thousands of vehicles. Automation can improve efficiency. Battery costs can fall, and margins can become attractive. But when demand weakens or prices fall, the economics can change quickly. The robots don't disappear. The building doesn't disappear. The debt doesn't disappear. And the factory still needs to produce enough vehicles to cover its enormous fixed costs. A Tesla factory doesn't make money simply because electric cars are the future. It makes money when the factory can produce enough electric cars at a low enough cost and sell them at a price that still leaves enough margin to justify billions of dollars in investment. That's the real game. Scale matters. Efficiency matters. Battery costs matter. Technology matters, and timing matters. So is owning a Tesla factory a license to print money? Not exactly. It's a massive industrial bet on electric vehicle demand, battery technology, manufacturing efficiency, and the future price of transportation. If the factory achieves high production volume, controls costs, maintains strong demand, and adapts to new technology, the economics can be extremely attractive. But if prices collapse, demand slows, battery costs rise, production falls, or the factory becomes underutilized, that same multi-billion-dollar facility can quickly become an extremely expensive collection of robots and machines. The most dangerous Tesla factory isn't the one that can't build enough cars. It's the one that can build hundreds of thousands of cars, but can't sell them for more than they cost to make. That is the real economics of owning a Tesla factory.